This video is the first in a series that will go over how to create 3D graphics in Pico-8, like what you're seeing right now. This first video will go over how to draw the walls, and in the next video we'll texture them. And after that we'll go into some more advanced geometry, so you can create more interesting 3D scenes. So first I'll give you a basic overview of how the algorithm works, and then we'll go through some sample code line by line to really hammer out the details. So basically how the algorithm works is we're going to loop through every X position on the screen, or every column of pixels, and for each one we're going to draw a vertical line of varying heights to represent the walls of the room. And the farther away the wall is, we're going to draw a shorter line, and the closer the wall is, we'll draw a longer line to give the sense of depth. So in order to find that distance, we're going to use a raycast. So the algorithm will do a raycast for every pixel on the screen, going out in different directions, and that raycast will look at every tile along its path, and as soon as it hits a tile that is solid or a wall tile, it will stop and use the distance that it's traveled to draw a vertical line based on that distance. So the question is, how do we find the distance from the camera to the wall along a ray? So let's go over the raycasting algorithm to figure that out. So I've got an example here. You can see the red dot is our starting position, our camera position. The white line is a ray that we're casting through the grid, and our goal is to look at every intersection along this line and see if there's a wall tile at that location. And if there is, we need to mark that down as our distance and then draw a vertical line on the screen to represent that distance. You'll notice some of the intersection points are marked with pink and some with orange. The pink intersections are the intersections along the horizontal axis as the ray moves to the right, and the orange markings are the vertical intersections as the ray moves up. And the key insight here is that the distance between any two pink markings is always the same. The same with the orange markings. The distance between any two orange markings is always the same. So we can use that to efficiently iterate along this ray, counting every tile, because we can simply add the same distance to our ray every time, and we know we will end up at the next intersection point, as long as we're counting our vertical and horizontal intersections separately. So when we first start, we'll be at this position, and we'll need to find our initial offset. So that will be this first pink marking and this first orange marking. And so then, once we have that as our initial offset, we're going to start the algorithm and say, alright, what's the smaller of the two? Because that will be the first potential intersection where we might hit something. So in this case, that will be the offset at this pink marking. And so in that case, we'll move right one tile, since we're on a horizontal intersection, and see if there's anything here. If there was something here, we would stop here and say, nope, this is where we've hit something. We will draw a vertical line here and move on to the next raycast. But if this tile is empty, then we will add the standard offset to our horizontal offset, so that will move it from this pink marking to this pink marking, because that's the next horizontal place where we might intersect something. So now we can start the loop over again and say, alright, what's the smaller of the two? Well, this time it's the vertical offset that is the closest distance where we might hit something. So since it's a vertical intersection, we'll move up one, see if there's anything there. If there was, then we would stop at this distance. Otherwise, we would add our standard offset to the vertical offset to move on to the next orange marking. So now that will leave us with our horizontal offset here and our vertical offset here. So the smaller of the two is obviously this one, which meaning we'll move to the right and add our standard offset. Again, move to the right, move to the right, move to the right, until our standard offset moves from this pink marking to this pink marking, leaving this to be the closest distance where we might hit something. So then we'll move up, add our standard offset to that one, and continue on in that manner until we hit something or go out of bounds, at which point we'll stop, record our last known distance, and draw the vertical line on the screen, representing the wall. So hopefully that made sense. If you have any questions or suggestions on how I could explain this better, be sure to leave that in the comments. I'm new to making YouTube tutorials, so I'd really appreciate that kind of feedback. But anyways, next we're going to go into a code example. I've got all this code uploaded on my itch.io page if you'd like to see it for yourself, link in the description. But anyway, let's get into it. So this is our raycasting algorithm. There's two sections here. First we find the intersection, and then check for collision. If there is a collision, then we'll draw a vertical line and break out of the loop. Otherwise, we'll loop back to the top and find the next intersection in a row. Now, in order to find that intersection, there's a bunch of variables here that we need to have set up beforehand to make this raycasting super efficient. So let's go over what each of these variables does. So this is where all those variables set up. First of all, this is where it starts. We're looping through every x coordinate on the screen, and we're going to do a raycast for each of those coordinates. To start the raycast, we need to find the position that we start at, which will be the player's position. And these x and y variables here is where we're going to keep track of the tile that we're looking at currently. And so every time we iterate through the raycast function, we're going to add to these x and y variables to find the next tile in the grid. The next thing we need to know is what direction we're raycasting in. So this function will use the angle the player is facing and the pixel that we're currently considering to determine the x and y coordinates of a vector that's pointing in the direction of the ray that we're trying to cast. And I've got it set up here such that it will produce a 90-degree field of view centered on the player's angle. So now that we've got the location we're raycasting from and the direction we're raycasting in, the next thing we need is the standard offset that we talked about earlier, the distance between any two intersection points, horizontally and vertically. That's pretty simple. It's just the absolute value of 1 over Vx and 1 over Vy that we just found here. Now the next thing we're going to need is some increment values. This will make it a little more convenient later on when we want to find the next tile in a row if we're moving horizontally, rather than having to check to see whether we're moving to the left or the right and add 1 or subtract 1 from our coordinates. What we can just do is add ix to x, and ix will be set up beforehand such that if Vx is greater than 0, it will add 1, and if Vx is less than 0, then it will subtract 1. If you're not familiar with this format, this is called a ternary statement, and it basically takes in a conditional, and if that's true, it'll return the first value, and if it's false, it'll return the second value. A little useful tool that can help make your code a little more efficient. Final thing we need to set up is the initial offset. Now we already found the standard offset, the difference between any two intersection points, but when we first start, the camera isn't necessarily going to be on an intersection point, it's probably going to be in the middle of a tile somewhere. So we need to find out what that initial distance is to get to the first intersection point, and then we can raycast to the grid efficiently after that. So I've got this nice diagram here. So we've got two different rays, and let's look at this example here. So if we're moving to the right, we want to find this first intersection point here, the distance to that point. In order to do that, we can find this distance here first, the horizontal distance from the camera to the nearest horizontal intersection point, and then divide that by Vx that we found earlier, and that will give us the distance along the ray rather than the straight horizontal distance. And we can do similarly for the y, find the distance from here to here, divide by Vy to get our first vertical intersection point. Now, if the ray is facing to the right, we'll want to find this distance, but if the ray is facing to the left, it'll look more like this, and so we'll need to find this distance instead, the distance from the current position to the nearest horizontal intersection on the left side. So you can see that reflected in the code, where if Vx is greater than 0, that means the ray is going to the right, otherwise it's going to the left. So if it is going to the right, we need to find the distance from the current position to the right-hand side and divide by Vx, otherwise we'll find the current position to the left-hand side and again divide by Vx. And similarly for the vertical direction, we'll find the distance to the bottom or the distance to the top and divide by Vy. And we want to make sure to absolute value this so that we never have a negative distance, because that wouldn't really make sense. Okay, so now we've got all of the variables set up. Let's go back over this real quick. So we've got a location that we're considering, the direction we're raycasting in, the standard offset, and the increment value that we're going to be using to move through the grid, and then the initial offset that we'll start off with. So now that we've got this initial offset, whenever we want to find the next intersection point, we want to find the smaller of those two offsets, and if the x offset is smaller, then we want to move horizontally through the grid. That will update our x position, and we want to also set our distance, that's what d is, our distance to the intersection point that we're considering, and we know that in this case OX is the smaller of the two, so we're considering that to be our next potential intersection point. But then we also want to set up for next iteration, we want to add our standard offset to our current offset, so that next iteration we'll consider the next intersection in a row. And so whichever one is smaller, we will update that accordingly, and then we can check for a collision at the coordinates x, y. And the rest of this if statement is just to check if we've gone out of bounds or not, because if we go out of bounds, we want to immediately stop and break out of the loop, so it doesn't keep looping into infinity. And if we do find a collision like that, then we want to draw a vertical line and break out of the loop. Now, for drawing this vertical line, well, we know we're going to be drawing it at the x position of I, because that's the pixel that we're currently raycasting at. So for both endpoints of the line, their x position is going to be I, and then the y coordinates of the two endpoints of the line will be 64 minus h divided by d and 64 plus h divided by d. D is our distance value that we found earlier. That is the distance to the intersection where we found a collision. And then h is just a variable that you can change to change the height of your walls. So if the variable is larger, this term will be larger, and so the walls will be taller. And by dividing by d, the larger d is, the shorter the wall will be, and so that will give us our sense of perspective. Now as for the color of the line, I've just got an array here that stores a list of colors, and so it takes in the map value that we found and looks for the corresponding color that I've defined in the array. So that way the different kinds of walls will be drawn in different colors. So that is the entire algorithm. Let's see it in action. We've got the different colors of walls being drawn. Farther away lines are being drawn shorter to give a sense of depth. And that's pretty much it. So if you have any questions, let me know in the comments. And don't forget to subscribe, because next video we're going to be texturing these walls to create the effect that I showcased in my last video with the Wolfenstein textures, and it's going to be really cool, so stay tuned for that. But in the meantime, that's all I got, so thanks for watching.